Hello everybody. This is our video solution to problem 4 from Quiz 12, Spring 2023, Math 302 at Cal State Fullerton. So in this problem, we have a long preamble. All right, this is basically giving you some extra theory that mimics what we did in class. We did it for very specific situations, but it turns out all of the proofs that we did will generalize quite nicely. So let's go through it. So we've definitely talked about the norm map quite a bit, and the norm map we looked at on the Gaussian integers and the Dedekind integers, z adjoin root -5. But you can extend this all the way to the entire field of complex numbers. And in that case, you'd end up with a map that looked like a plus bi goes to a squared plus b squared. And this map is going to be multiplicative still. Fantastic. The proof of that, by the way, is actually quite simple. So another way of writing this map is to say if I had some z, it would map to z times z bar. All right, where this bar is the complex conjugation map, which is itself multiplicative. And so if I have n of zw, this would be zw times zw bar. But again, the conjugation map is multiplicative, so this would be z, w, z bar, w bar, and then I can rearrange this, zz bar, w bar, which is now the norm of z times the norm of w. Okay, so we have this norm map that's multiplicative, and then we say if d is some positive number, then n is going to, d here, right, is meant to be an integer, right? So here d is an integer. So n is going to restrict to a multiplicative map. So we use the same n here, but now instead of looking at all the complex numbers, we look at z adjoin root -d. So in class, we specifically looked at root -1 and root -5. And so this map is just going to send a plus b root -d to a squared plus db squared. Fine. Again, we can show that the norm of some number is going to be 1 if and only if it's a unit. All right, and this again, you go back to this complex conjugation version if you wanted to prove that. I'm not asking you to in this problem, but so I would know that the norm of z, of course, that's supposed to possibly equal 1. This is equal to z times z bar. So z times z bar equals 1. Well, if I knew that z bar equaled 1, that would mean that z is a unit, because look, I have an inverse, namely z bar. On the other hand, if I know that z is invertible, then I'd be able to say, well, I know that n of z w, right, we'll just call it inverse, zz inverse is going to equal n of z inverse. But n of z inverse, right, this is of course equal to n of 1, which is 1. So 1 is equal to this product, but oh, how is that going to be possible if I have non-negative integers? Well, only if both of them are equal to 1. Okay, and so that tells me that the norm of z is 1 if we know that z is a unit. All right, so that's true. In class and on a quiz, so we explored the situation where d equals 5 and d equals 7. Yeah, okay, so on our first quiz where we examined the standard, we actually handled this additional case. And, right, again, in class we looked at d equals 1 and d equals 5, but on this quiz, we had these so-called Glesser Glesser integers, right, where d was equal to 7. Okay, and we showed that we didn't have a UFD, right? You could have elements that had multiple factorizations into indecomposable elements. And so your problem this time is to find some d not 5 or 7, right? Something we haven't covered, such that z adjoin root -d is not a UFD. By the way, you don't want to use 1 because, well, actually we know the Gaussian integers are a unique factorization domain. Okay, so then a little clarification, right? We want to find an element of z adjoin root -d with two distinct factorizations into indecomposable elements. All right, so we got through the preamble. Now we can try to do it. In lecture, we actually had this nice little Desmos uh, app, if you want to call it, all right, where we were actually looking at the division algorithm and trying to figure out if we could tell graphically where we were going to start having problems with the division algorithm. And of course, if we can't perform the division algorithm, then we lose like all that stuff down the line, right? Because remember, we use the division algorithm to get the Euclidean algorithm, which we use to get Bézout's lemma, which we use to get Euclid's lemma, which we use to then prove the fundamental theorem of arithmetic, right? That is that we had a UFD. So knowing that we don't have a division algorithm, well, it doesn't exactly rule out that we could have a unique factorization domain, but it certainly suggests that we might be in that situation. And what we were able to show is that the first time when we're dealing with this situation, z adjoin root negative d, the first time we have any sort of potential problem is when d is equal to 3. So I'm going to use that as my D here, but you might have used a different D, and probably the work you do is going to look fairly similar. So I'm going to choose D equals 3. All right. And so that means I'm looking at Z adjoin root negative 3. That is kind of gross. I'm going to call this alpha. So alpha squared is negative 3. And very similar to what we did for the Dedekind integers, I'm going to look at d plus 1. So, and we did this with the Glesser integers too, right? There we looked at 7 plus 1. Dedekind integers, we looked at 5 plus 1. Here I'm going to use 3 plus 1. So 3 plus 1 can be factored as 2 times 2, but it can also be factored as 1 minus alpha, 1 plus alpha. All right? And of course, you could just do, I mean, the left side, I assume everybody believes that. The right-hand side, of course, 1 minus alpha, 1 plus alpha, you can distribute. It's a difference of squares, so this is 1 minus alpha squared, but alpha squared is minus 3, and 1 minus the opposite of 3 is 4. Okay, but now we need to verify that we actually have indecomposable elements. I'm going to make a general argument that's going to hit all 3 of these different numbers at once. So claim no element of Z alpha has norm 2. Okay? Now, why is that relevant? Well, first, every one of these, 2, 1 minus alpha, and 1 plus alpha, if I compute the norm, let's see, the norm of 2 is 4. The norm of 1 minus alpha is 4, right? 1 squared plus 3 times 1 squared. And the norm, is equal to the norm of 1 plus alpha. These are all equal to 4. So if I could take any one of these and factor them, okay? So let's let, I don't know, let's call it P, okay? Be one of these, okay? I don't know which one, I don't care, right? It could be any one of them. And assume P is equal to Z times W, where Z and W are in Z alpha. Okay, so assume we have a factorization. Of course, we're trying to show that all of these are indecomposable, so any factorization should have a unit in it. And we know that the units, right, that's this up here, the units are characterized by having norm 1. So since I know that the norm of all of these is 4, I know that the norm of P is 4. And the norm of P is the norm of Z times the norm of W. Well, how can I have 2 non-negative integers multiply to give me 4? Well, there's only a few different ways. I could have 4 times 1 or 1 times 4. And in either of these cases, one of the two has norm 1. So either one of these would imply that Z or W is a unit. Okay, and then I'm fine in that case. Okay. Now there's one other way to do it. I could do 2 times 2. And this is why I want this claim that no element of Z alpha has norm 2, because if that's true, then I can say this line is impossible. And if this is impossible, then I know I must be in one of the above two situations, in which case I know one of the factors is a unit, and that will imply that P is indecomposable. Okay, so we just need to prove this one statement, and we get all 3 indecomposability statements at once. So if, we can use a different letter. Q, say, is in Z alpha, such that the norm of Q, well, man, I don't even really want Q, right? I want to write it down explicitly, right? So let's write Q as something like A plus B alpha, because that's what things in this ring look like. So then I would have the norm of A plus B alpha is equal to 2, but the norm of A plus B alpha is A plus 3B squared. Okay, so this tells me that A plus 3B squared is equal to 2. All right, well, I need to find A and B here, and they have to be integers, right? So if B is not 0, then B squared is at least 1. And that implies that 3B squared is at least 3, and that implies that A squared plus 3B squared is at least 3, and 3 is greater than 2. So if B is not 0, then it's impossible to get, I wrote here A, that should be A squared. It's impossible for us to get a norm that is 2. And right, it has to be at least 3 if B is non-zero. Okay, fine, so B has to be 0. But if B is 0, well, then I get rid of 3B squared. I have A squared is equal to 2. And that's just not possible. 2 is not a perfect square. This is a contradiction. Okay, and those were the only possibilities. So that completes the proof of our claim. And therefore, we conclude that 2, 1 minus alpha, 1 plus alpha are indecomposable. And because of that, we know that Z alpha is not a UFD. We have found an element that has more than one factorization into indecomposables, namely 4 as a product of 2's, or as 1 minus alpha times 1 plus alpha. Okay, hope that answers at least some of your questions. We'll see you next time.